Okay, yeah, I will begin by thanks to the organizers for a wonderful conference and for the opportunity to talk here. And here is the heroes of my talk, two graduate students from MIT, Josephine and Mark. They are also here. And if there are questions I cannot answer, please ask them. And so the talk is based on two papers with Josephine, which appeared last year, and also some unpublished work with Mark and Josephine together. And also there are some unpublished work by Cassini, and we may join forces together with also with Veronica, etc. And also there are related papers by various authors. So let's consider, suppose you have a quantum system. Let's divide it into two parts, A and B. And let's start with the initial state, which are a product state between A and B. And now the system will evolve, suppose the system evolve under some Hamiltonian, and the Hamiltonian involve some interaction between A and B. And then such an interaction term will generate entanglement between A and B. Okay? A basic question in quantum mechanics, also a question of great interest from the point of view of quantum information and quantum computing, is how fast can entanglement be generated? Suppose I give you a typical Hamiltonian. And actually, for the most physical systems, there's a slightly technical issues. For most systems, we work actually with the local Hamiltonian. And now, if you imagine these this A and B are actually two regions, of the series defined in some space, then actually for local Hamiltonian, they don't directly couple they only couple a small part of A and B. They only couple, the region of A and B, which are close to each other near the boundary, and defined by some short distance cutoff. So in other words, the Hamiltonian which couple A and B is essentially only the part which involving C and D. And this delta is the UV cutoff. And so and the measure of the entanglement between A and B, is the one measure, at least one measure of the entanglement between A and B is the entanglement entropy of A, which when you integrate out the B. And in the context of spin system, there exists something like called a small incremental entangling conjecture, which has been around for quite a few years, but was only proved last year by the last three authors, by the last three people here. And the statement is that for any Hamiltonian, for a spin system, the derivative of the entanglement entropy is bounded by this quantity. And the remarkable thing about this inequality is the right-hand side only involving this quantity D, and the D only involves the dimension of the Hilbert space of the C and D. So only involve the part of the Hilbert space which are coupled, by your Hamiltonian. Okay. And this is just the ordinary operate norm for the Hamiltonian. So this is a spin system, so you have a finite norm. So of course, an obvious question, so the remarkable thing is that this is proportional to the logarithm of the dimension of the Hilbert space of C and D. And of course, the larger question is that for general quantum system, for quantum system which does not have a finite Hilbert space, what would be the analogous statement? And in such a case, for example, the norm of a Hamiltonian does not make sense, etc. And so in this talk, we will describe some hints, from holography and string theory on this question. So here we will consider a simple setup, which is called, so the first thing you want to do is you want to set up a time-dependent system. So a simple setup is the following. Let's start with a QFT in the ground state. And then for a very short time, inject a uniform energy density. And this way, you can create an initial state which is homogeneous and isotropic, so it's very simple. But we want also inject the energy density in a way so that the entanglement property of this loose state, this finite energy density state, is the same as the vacuum. And then you just let the system evolve, and they will typically involve to, say, thermal equilibrium. And then what we want to do is we want to just take some arbitrary region, which we call A. So let's just integrate out everything else and then calculate and see how the entanglement entropy of A evolves with time. Okay? So this question should give us some handle on this issue I outlined earlier. And also this is a question not only, say, of interest from the point of view, say, of basic quantum mechanics, and this is also a question of interest, say, for many field of physics which thermalization is relevant, like QCD or some area of condensed matter physics. So it's convenient, say, to define the following quantity, say the entanglement entropy as function of time subtracted by the entanglement entropy at t equal to 0. Then by definition, at t equal to 0, then you delta S equal to 0. And so eventually the system will approach equilibrium. And in equilibrium, even though the system remains a pure state, but macroscopically, it will behave like a thermal state. And with the entanglement entropy disguised as thermal entropy. So this is our familiar things related to the black hole physics, say in the guise of the information paradox. And so that means that in the equilibrium, this difference of the entanglement entropy with the t equal to 0 will be proportional to the volume of the region and the times of the equilibrium entropy density. Okay? And this volume dependence is crucial because it tells you that essentially all degrees of freedom inside, because the number of degrees of freedom for typical many-body system is proportional to the volume. And so this tells you that essentially all degrees of freedom inside A become long-range entangled with those outside A. And in contrast, a defining property of our initial state, which is the same entanglement property as that of the vacuum, essentially long-range entanglement. So the degrees of freedom which are long-range entangled initially is essentially measure 0. And so through this quench process, and so I use color coding there, and now essentially everything inside A is entangled with everything outside. And so this set up a good process for us to probe the question, how does entanglement, say, generated through time. So here there's a classical result of the Calabresi and the Cardi, which they look at this problem in 1+1 dimensional CFTs. So in 1+1 dimension, so let's just, so the simple case, you just consider the segment of the region. So the region A is just a segment. Say let's take it to be length to R. Then they find the remarkably simple behavior. So they find that this delta S divided by equilibrium entropy is a change with time is essentially just a straight line. And their analysis does not apply to too early time or too late time. But for the most of the time, it's just like a straight line. It's a simple linear growth. And in particular, if you normalize the vertical axis, which is the change of the entanglement entropy by the equilibrium entropy, and the horizontal axis of the time, and divided by R, and then you find the slope is exactly equal to 1. So that means in this unit, in this 1+1 dimensional, in the class of these 1+1 dimensional CFTs, the quantity I mentioned earlier in the unit of those quantities is exactly 1. So ds dt is exactly 1. And also another remarkable thing is that they found that this behavior can actually be reproduced by free particles. So this is a result for general CFTs. In principle, can be strongly interacting. But they find actually this result can also be reproduced by free particles. And they come up with a very simple model as follows. So imagine, so at t equal to 0, we inject a finite energy density into the system. But so let's imagine that what that energy density does is to create a pair of particles. Okay, so essentially you create a finite density of particles at the beginning. And then those particles, suppose those particles are massless, then they will travel at speed light. And let's assume that at the beginning, those pair produced particles, say they're maximally entangled. And then you can easily work out the entanglement between A and its complement just to see how many particles hit region A, and how many pairs with one of them hit region A and one of them hit outside. And that way, then you register, say, 1 unit of entanglement between A and B. So such a simple model, particles propagate free, then reproduce exactly this behavior, and with the slope 1. And here, and in this model, you can understand the slope 1 from the speed of light is equal to 1. Okay. So, but these spatial techniques in one spatial dimension cannot be applied to higher dimensions. So in higher dimensions, the question we are looking at is very complicated. Say, for example, equilibration process is in general very complicated, non-equilibrium many body dynamics, generally out of theoretical control. And entangled entropy is also notoriously difficult to calculate, even for simple regions in the vacuum of a free theory, not to mention, say, for general regions in interacting theories far from vacuum. So whenever you encounter some difficulties in field theory, so we have a used tools, and instead we go to string theory. So our work is a follow-up of is built on the many earlier work in terms of understanding quench, a global quench in the holographic context. For example, the Hubini, Ragamani, Takayagi was the first paper of doing that. Okay, so in the holographic context, a quench just can be described by a Vaidya solution. So essentially, imagine at t equal to 0, you insert a uniform density of local operators. And then from the Bach point of view, and you inject some energy, then this thin shell of the matter will collapse to form a black hole and form a horizon, etc. So the full space-time will contain a region containing a black hole with horizon, and the region which before the thin shell would be just pure ADS. And also in the holographic context, it's easy to calculate entanglement entropy. Yeah, it's comparably easier to calculate entanglement entropy, which is, as Mark reviewed earlier today, you just calculate the extremal surface ending on the region you are interested in. And then the entanglement entropy is given by this, the area of the extremal surface. So our goal is just to calculate for some region how this SA change with time, essentially just how the area of the extremal surface changes with time. And so let me introduce some notations that we'll call the boundary of this region sigma, and then the area of this boundary we'll call A sigma, and the volume just VA. And also I will introduce R, which is the, say, characteristic size of the region. And I'm interested in the long-distance infrared physics. So I will be interested in the, say, the limit R is very, very large. Okay, so the gravity description just the corresponding you find this extremal surface, say, in some time-dependent geometry. And so here is an example in the Penrose diagram. Say if you have some surface at early times, so this is one typical extremal surface at any time. So in this Penrose diagram, all the spatial direction has been suppressed. So the radial is time direction, and then there's a radial direction in the Bach. So this is the initial, so this is extremal surface at very early time, and then intersect with this shell at a very early time. So there's only very tiny part is inside the black hole region. And so if you wait some time, then eventually this extremal surface will evolve, and at a certain point, this extremal surface actually will go behind the horizon, and will enter the shell behind the horizon, and then go back to the boundary. Okay. Anyway, so the way you found those extremal surfaces, you fix the condition at the boundaries at some time t, say at some, then you fix the shape and the sides, and then you find the extremal surface. But equivalently, you can also find the extremal surface by specifying the location of the tip, say, of the extremal surface in the Bach, and also the boundary condition at the tip. It turns out that this second way actually gives you a lot of additional insight. And so in general, this is actually this is a well-defined geometrical problem But still, in general, it's a rather complicated problem involving partial differential equations, etc., to determine the time evolution of extremal surfaces. But remarkably, in the large size limit, it turns out that this problem can actually be simply solved by mapping to a critical phenomenon in the gravity side. So let's imagine the following. Let's slice the Bach geometry by the constant radial slice. Okay, so this is one constant radial slice. So if you go along this slice, then the time changes. So it turns out, suppose if you consider the extremal surfaces starting with the tip starting on this slice, then they will evolve and go to the boundary. So turns out actually there's a critical time. Before this time, then all extremal surfaces starting before this time will end at the boundary. But after this critical time, all extremal surfaces which are starting from this point will go to the black hole horizon, will never reach the boundary. And then you have a critical extremal surface, will then go to t equal to infinity and I equal to infinity at the boundary. And essentially, if you're interested in the large size limit of the extremal surface, and that is just essentially controlled by this critical extremal surface. Okay? And remarkably, this critical extremal surface can be found out analytically, despite the general problem is a complicated one. And so by looking at this critical extremal surface, we can determine the large R, large time behavior. So by doing this, and you can actually find, say, the large size limit, say the R is much larger than the Fallot equilibrium temperature, 1 over the Fallot equilibrium temperature, then you find that there are actually 4 scaling regime. So at the beginning, there's a quadratic growth with time, and then there's a linear growth, and then some other regime, and then eventually will saturate. Okay, eventually saturates. So I will just focus on the linear growth region. So in the linear growth region, the behavior is very simple. So it's just given by, say, it's a linear in time, but it's convenient to parameterize this dependence by the area of the surface and the equilibrium entropy density. Okay. And this formula turns out to be remarkably universal, and it's independent of the shape of the region A you consider. And it also is independent of the holographic series under consideration, the nature of the equilibrium state, and also likely the thermalization process. Even though here we are only considering, say, a quench, some other process was also considered by Hartmann and Monsignor, and the same answer was obtained. And this VE is a dimensionless number which actually characterizes your Fallot state. Say if your Fallot state, say, have some chemical potential, then you will have a different VE. Okay. So from the gravity point of view, this critical extremal surface corresponding to the linear growth regime turns out to be given by some surface which just go along a constant radial slice inside the horizon. So this constant radial slice inside the horizon is a constant time surface inside the horizon, because this is inside the horizon. So this is, in some coordinate, for example, if you write the ADS black hole holding in some kind of coordinates, and then this is corresponding, then this critical extremal surface will run along a constant Z surface once it enters the black hole region. And this radial and this location can be found by just extremalize this function h, which multiplies dt squared and divided by z to the power 2d, and d is number of spatial dimensions. So you do this minimization problem, which always gives you some surface inside the horizon, and then you find this velocity. Okay, you find this velocity, and this zh is horizon side. So now, also this formula tells you that despite we are looking at the non-equilibrium process, but this dimensionless number VE is actually determined by equilibrium state, because only determined by the physics of the black hole. Okay, and there's another interesting feature of this formula, is that this linear growth formula, I can slightly rewrite it as the volume of A, of the original region enclosed by A, subtract the region with the boundary of A slightly shifted. So slightly shifted in all orthogonal direction by this VE times T. So imagine you start with the boundary of original A, and you shift inside by VE times T, orthogonal to every point. And then so this region, the white region, then defines this A minus VET. So this delta ST can also be considered as a difference between the volume of these two. And then this can be naturally interpreted as if the growth of the entanglement comes from a tsunami wave of entanglement propagating from the boundary to the inside, and the region with the degrees freedom in the region covered, which is the orange region here, covered by the wave, now become entangled with those outside A. And those regions not yet covered, which is this white region, are not yet entangled. Okay? So this is also natural from the point of view we consider evolution of a local Hamiltonian. When you have a local Hamiltonian, you only couple degrees freedom nearby, and so it's natural that somehow entanglement may propagate locally. Okay, so this VE essentially defines, so can be interpreted as this tsunami velocity, okay, a tsunami velocity, and then you can find this explicit value. For the threshold, ADS threshold, then corresponding to a neutral system, and then that gives you a following expression. So D is the number of spatial dimension. So from number of spatial dimension, you construct this eta, and then you construct this formula. And this formula has the following property: for D equal to 1 is given by 1, the same as found by the Calabresi and Cardi. And then for D equal to 3, etc., they become smaller and smaller, and then become 1/2 at D equal to infinity. And when you turn in a chemical potential, then you reduce this number. And now you can just study. So, of course, we consider relativistic field theory. This VE should be constrained by causality. But how it is constrained by causality is actually not trivial to see. It's not simple to see. But we can, now we have this formula which essentially applies for all gravity examples. Then you can just check what is the behavior of this VE, say for all possible gravity examples you can find. And then we found that they're always smaller than this threshold value. It's always smaller than this value. And in particular, the low energy conditions are important. And if you violate this, then you can go beyond this. And so this suggests this actually threshold value might provide the upper bound. Okay. And also, to give you a perspective, we can also compare this to the story of the free particle streaming. So again, follow the story of Cardi and Calabresi. Let's assume that T equal to 0, what this energy density does, injected energy density does, is just to create, say, the massless particles with local entanglement correlations. Okay, and then then the entanglement spreads when the photons spread. And then, so in higher dimension case, of course, then then all these particles will propagate on the light cone, inside the light cone. And then you can show with this simple model, again, you get, at early time, you get a shape-independent linear growth with some VE. And in particular, for D equal to 1, the velocity is equal to 1, just as Calabresi and Cardi found. And this result was found earlier in the holographic context by Lopez and the co-authors, which I quoted earlier. And for D equal greater than 2, then you found that the streaming velocity is given by this formula, and it's always smaller than 1. Okay? And in particular, it's actually smaller than the value we see from the gravity side. So this tells you that in strongly coupled systems, this entanglement tsunami appears to propagate faster than those from the free particles traveling at the speed of light. Of course, the free particle is crucial here. So this tells you that the interaction must be very important in generating entanglement. And also to have some perspective, say let's consider D go to infinity limit, then this gravity result goes to 1/2. But this free particle streaming answer is inverse proportional to the square root D and goes to 0. So when you go to higher dimensions, then the interaction becomes more and more important in propagating the entanglement. And also this naturally suggests that maybe we can consider not only in the linear regime, and consider, say, the entanglement growth in the generic process and in the generic regime. And then we can introduce this dimensionless number, which we call this RA, and which is the dSdt divided by equilibrium entropy density and the area of the region. And this is dimensionless number, which in principle you can compare among regions of different shapes, size, and system of different number degrees freedom. Yeah, because those things are already be divided out, and then you just get the dimensionless number you can compare across different systems. You cannot do so for directly for the dSdt. So again, indication from the gravity is that after the local equilibration, say for the time greater than the 1 over the temperature, 1 over the equilibrium temperature, this appears to be always smaller than this value I showed earlier. Okay, so if this gravity result is suggestive, then we may have an inequality like this, say for general relativistic quantum field theory, say some dimensionless number times times entropy density, equilibrium entropy density, and then times the area of the region. So at first sight, the appearance of the area of the region here is a little bit unintuitive, but this is actually very natural. If you think about this small incremental entangling conjecture, and there, as I emphasized earlier, on the right-hand side, what's appearing is log D, is the part of the Hilbert space which are directly coupled by a local Hamiltonian. Yeah. And that can be considered as a counterpart of our A sigma here. Yeah, because in the quantum field theory, they only intact near the boundary. And then this SEQ then plays a role, say, of the norm of the Hamiltonian. Okay, yeah, so let me conclude. So let me just quickly show you some future directions. And yeah, thank you.
So does the analysis depend on whether there is a firewall or not? And if there is, would that be modified?
Yeah, I think the results, so we can do it backwards. Say, suppose we can find a theory which have this kind of behavior. Say let's do a strongly coupled theory. Suppose we are powerful enough. Say we can find this behavior, and then we compare with gravity. And here the discussion assumes no firewall, and so that might be used as evidence against firewall, at least at some operational level. Yeah.
Has the VE for supersymmetric theories, like super Yang-Mills theories of some kind with matter, have they been related to some other kind of supersymmetric quantities? Has anybody tried to compute them?
No, actually, right now we know very little about this VE, or where it comes from, and the only thing we know is that it must be at some point constrained by causality, but we don't really have idea how this can be directly constrained by causality. And yeah, so this free particle example was an attempt to have some intuition for that.
Raphael?
Is it correct that your extremal surfaces always cross the horizon when the horizon is less than a scrambling time old?
Yeah, here it's always less than scrambling time.
Well, because if so, then this does not constrain firewalls in any way.
Yeah.
Because the claim would be that firewalls form after that.
Right. That should be careful. So at our level of discussion, which is involving a pretty, it's just classical geometry in the bulk, and so that scrambling time does not, at least does not directly appear in this kind of calculation. But there's a paper by a couple of papers by Schenker and Douglas Stanford, which they look at this how this kind of process can be related to this scrambling time, and there are some connections in that kind of.
Well, about more physical intuition in future directions of the speed of entanglement, I would propose the first step, for example, consider if this speed could be more fundamental than the speed of the zero mass particles. That's it, the speed of light. I think would be very interesting. Because I think entanglement is very profound. It's very deep, very profound.
Right. I'm not sure whether this will replace the speed of light, but certainly this is, if there's something, if we understand it better, it may appear in other places. It may appear in other places, so then can be a very useful quantities to understand for field theory.
Last question, and then we have to move on.
No.
Oh, okay. Thank you very much.